All right. So let's start with what we did last time. So, and this is a discrete probability models. So, discrete probability models. In fact, we will not cover any besides discrete probability models. So at some moment we will talk about the continuous random variables, but we will not talk about continuous models, and they are just more complicated. So discrete probability models is just a number of outcomes is finite. So omega, it's the set of the outcomes. It's finite, or countably infinite. And so kind of all the intuition is usually it's enough to just look at the finite case, so something like that one. So I don't know, n, the largest element, but sometimes we will look at the situation when we have an infinite number of outcomes, and this is the situation like when you throw a coin and just count the number of say tails before you see the third head. Right? So in this case, the potentially can be infinite, any number of the outcomes. So you cannot get a upper bound on this. Right? And in this case, kind of everything can be described by the probability mass function. Probability mass function, and this is just a probability of one particular outcome. So it's probability of so we will write it P of omega I. So P of omega maybe just P of omega. And this is just a probability of omega. And so probability of a specific outcome. So if we would have uncountably many outcomes, then in this case it would not be enough to just look at the probability of each individual outcome. So because it could be zero, but it's not describe everything. But in this case, just kind of every probability of every event can be written as a sum of the probabilities of omegas for omega which belongs to this event. So just kind of if you want to figure out what's the probability of event, we just sum the probability of all outcomes in this event, and it's clear that it gives the result. It would not work for uncountable spaces, probability spaces, because the sum would not be defined. Kind of, you would need to define an integral, and to define an integral, in principle, you need to talk about something like a density, or just kind of, so you just need to define what is the integral. So kind of, it's a big theory, theory of the integral. And so we are not going to do in the details of this. So this is graduate course in probability. And just look at this particular case. And what we can say about this case is kind of that the requirement on this probability mass function is that probability of omega, so it should be have two properties. Probability of omega should be greater than or equal than 0. And second thing is that so for any, so here's this signs for any omega. And second thing that the sum of probabilities should be equal to 1 if you sum over every outcome. And so kind of if the sum is all outcomes, then the kind of a probability of the whole space should be equal to 1. So now these two requirements are basically just to satisfy Kolmogorov axioms, and this formula it's essentially the third Kolmogorov axiom. Right? So probability of A kind of you can think about as the union of the union of all outcomes in A. Right? So it's just kind of, and so this formula just reflects the third axiom of Kolmogorov. So it's a disjoint union of events, and so probability of A is equal to the sum of the probabilities of these events. And so now in practice, so kind of if you want to build a model, so you need to define this probability mass function. And well, it's easy kind of, it should be negative, but it's not so easy sometimes to satisfy the second condition. So in practice, it's usually kind of you define the weights of the outcomes. And it's something like you define the weight of the outcome omega, which should be non-negative. So non-negative, negative weight. And after that, define the probability of the outcome as weight of this outcome divided by the sum of the weights over all outcomes. So this is something like a usual practical device how to define this this probability of each outcome. So here's an example, right? So how it works. So the simplest kind of case, which we already covered, would be just to assign equal probability to each outcome. So the example. So if you assign equal weights, so for example, if you assign weights equal to 1 to each outcome, right, and number of outcomes so it's is equal to n, then the probability of omega is equal to 1 divided by n, right? And we are back to this rule, kind of the rule by Laplace, that the probability of each event is equal to the number of outcomes in the event. So this sign is the number of outcomes divided by n, right? So by the total number of outcomes, so because kind of, well, so what is it? So I'm skipping a step here, which I don't want to do. So just kind of this step is that the sum of omega belonging to A of this P of omega is equal to sum of the omega belonging to A of 1 divided by n. And so from this line, and sum of n, so this is the number of elements in the sum, so divided by n. And so this is a Laplace rule. Laplace definition of probability. And so this is the simplest example. So kind of we already seen it. So for example, if omega is equal to 1, 2, 3, 4, 5, 6. So this is the number. This is just toss of a die, right? And A is equal to say 1, 3, and 5. Then in this case, the probability of A will be just equal to how many outcomes here. So 3 divided by 6 number of outcomes in the omega, so it's equal to 1/2. So in just this example, I give you just to give an alternative example. So example 2, it will be just a loaded die. So loaded die. And we will think about that the probability. So we just want a model, and the model will say that the probability of each outcome should be proportional to the number on the die. So we want that the probability of the outcome proportional to the number seen on the die. So the probability of 6 should be larger than probability of 1. It should be 6 times larger. So this is kind of what we want. So how we could define it? So we define it by kind of defining so the weight of the outcomes. So weight of the omega should be proportional, equal to this number seen on the DAM. So for example, so it's the previous example. So here's omega is equal to 1, 2, 3, 4, 5, and 6. So this is our outcome. So and we'll say that weight of 1 is equal to 1, weight of 2 is equal to 2, weight of 3 is equal to 3, and so on. Weight of 6 is equal to 6. So these are weights kind of assigned. So because we want the probability proportional to these numbers, right? So, but here it's a weights and they don't sum to 1, right? So and we use our rule kind of how to define the probability. So probability of 1 will be equal, okay, weight of 1 divided by the sum. So divided by omega, weight of 1 plus weight of 2 plus so on plus weight of 6. Just this is we're normalizing the weights by dividing by their sum. So now if you sum this thing together, 1, 2, 3, 4, 5, 6, then we'll get 21. Right? So something like a formula 1 times 1 plus 6 multiplied, so 6 times 7 divided by 2. Right? So this is a formula for arithmetic progression here. So it will be equal here to 1 divided by 21. So probability of 2, you get same thing, so kind of, but weight of 2 divided by weight of 1 plus so on plus weight of 6. So in this case, it will be 2 divided by 21 and so on. Right? So kind of in this way, we'll get the thing that we wanted. Right? So we will get the so probabilities which are proportional to the number which is on the die. So in this case, it will be 6 divided by this sum. 6 divided by 21. So in this way, you ensure that this is proportionality holds, and also that the sum of the probability is equal to 1. And this is absolutely kind of standard kind of trick, kind of which is used to define some nice, interesting probabilities mass functions. And so now in this case, so let us look what's the probability of this event A. So right, so event A was that A is equal to 1, 3, and 5. So in this case, we'll see that probability of A is equal to the sum of the probability of 1, probability of 3, and probability of 5. So it's 1 divided by 21 plus 3 divided by 21 plus 5 divided by 21. So what's the question? Chapter section, it's not considered in the textbook. Sorry about that, so, but not considered in the textbook. So this is just something that which I added to this because kind of I'll see it's constantly kind of, so it's defined and kind of it's useful, I think. So, but the discrete models are considered kind of in the textbook. All right. You can find it in the lecture notes. Okay, so now the sum is what's this is equal to 9 divided by 21. So it's equal to right, so 9 divided by 21. So 3/7, right? So slightly smaller, slightly than 1/2. Okay, so just kind of okay. So now let us okay. So question about this. Now let us get back a little bit to the material in the textbook, and so let us look at the simple probabilities laws. Right? So simple probability laws. So what consequences we can get from the axioms, and kind of also kind of, since we're working with the discrete probability spaces, we will not really use the axioms, but we use this idea that the probability of each event can be written as a sum of the probability of the outcomes. In general, we cannot do it, so you need to somehow work the axioms. But in this case, we can do it, and we can get several laws. So one of them is a complement law. So it allows you to calculate what's the probability of a complement. And probably, I guess, well, kind of, many of you probably seen it before. So it just says that probability of a complement of event, probability that something do not happen, is equal to 1 minus the probability of the event. So probability of AC is equal to 1 minus probability of A. Right? Right? The second law, addition law. It just describes what happens if you want to calculate the union, the probability of the union of the two events, right? And now we are talking not about the union in which the two events, they are not disjoint. They can be, they have non-empty intersection, right? And so it's equal to probability of A plus probability of B. So this is if they would be disjoint. But after that, you also need to subtract probability of A intersect B. Right? Then maybe kind of another law, kind of, it's really not a law, it's kind of just an equality. It says that if A is a subset of B, then the probability of A is of course smaller or equal than the probability of B. So if in addition to outcomes in A, there are other possibilities in B, then the probability of B is of course greater. So now, and again, so to get it from the axiom is easy, but it's kind of, well, you need to work. But to get it from the, just for the discrete probability space is very easy. So let's look at the first two laws, so how you can get them. So for the complement law, so you just write, say, probability of A plus probability of A complement. So this is something like a maybe proof or something like that, or just kind of explanation of this thing. And write, okay, so this is the sum of the probabilities of outcomes for omega which are in A. Right? And you add probability of outcomes for omega in A complement. But after that we say, all right, this is covers everything. So it's equal to the probability of, this is equal to the sum of the probabilities of omega for omega, which is everything. So kind of it covers all possible outcomes. And this is by our one of our conditional axiom is equal to 1. And so we'll see probability of A plus probability of C is equal to 1. And this is exactly the first law. And the second law is actually works well, kind of with simple calculation. So this is the first. This is the first law. The second law is kind of, so also kind of do the similar thing. So let's look at probability of A plus probability of B. So now, and write similarly. So it's probability, sum of the probability of outcomes where outcomes belongs to A, plus sum of the probability of outcomes where outcomes belongs to B. And so now we'll need to think about what is it. So, and here something which is called Venn diagram is useful. So you kind of, you draw it and see this is A, this is B. Right? You look at all outcomes in A, all outcomes in B. And so these are outcomes. And okay, so when you take this sum, you'll cover all outcomes in union, right? So everything in union of A and B is covered. So it's equal to sum of the probabilities for every outcome in the union of them. Right? So everything inside. But some of the outcomes, if you do this sum, if you do this sum, right, big sum, then you see that some of the outcomes both in A and B, right? So some of them inside of the intersection, right? And if you look at this sum, you covered them only once. But if you did the sum, which is the addition of this sums, right, then you covered them twice. Right? So you covered them when you counted this here in the first sum, you covered it also when you did the second sum. And here you just did it once. And so here, these outcomes will kind of counted more times. So you'll need to add them. So again, right? So here's probability of omega, where omega belongs to A intersect B. So I'll need to do this additional sum because in the original sum of the two sum I covered them twice. Right? Now that's okay kind of right now, but right now I'm writing that this is equal to the probability of A union B plus probability of A intersect B. Right? And now if I look back kind of on my law, right, so this is exactly what I needed to prove. Probability of a union is equal to the sum of a probability minus the probability of intersection. So the probability of a union is equal to this thing minus the probability of intersection. Okay, so this is kind of how you prove additional law if you kind of allowed to work with the with sums. Okay, so if you're not allowed, then well, you need to go to the axioms and try to prove it using the axioms. It's not very difficult, but kind of it's easy kind of, but all right. But need to be accurate to do it. Right now, right. So what about if you have a? So this is an example of something which is called inclusion and exclusion laws. So you kind of when you try to calculate probability of a union, then you did probability of A plus probability of B, but after that decided that you overcounted. So some outcomes were counted twice and you subtract something. Right? So you subtract the probability of the intersection. And so now it's kind of, it's a more general. So if you have three things, so probability of A, B, and C, then okay, so the picture in this case, it's like that. So, and then you're saying, all right, so how I calculate this probability of A union B union C? Okay, so I'll count everything in A plus everything in B plus everything in C. Right? That means that I'll take the probabilities of every outcomes in A, take every kind of outcome in B, probability of every outcome in B, probability of every outcome in C, and add them together, bunch them together. And the same problem as before arises, right? So some outcomes will be counted twice. So I'll subtract them. I say minus the probability of intersection, minus the probability of intersection A and C, minus the probability of intersection of B and C. So I removed this kind of thing. So I know that I counted these outcomes here, both when I counted A and C. So I need to kind of remove overcounting. Right? So I did it for this thing, for this thing, for this thing, for this thing. But now I'm looking at the outcomes which inside the intersection of all three of them. So now when I did the original sum, I counted them 3 times. Right? Right? So every outcome in the intersection of A, B, and C, I counted them 3 times. Right? When I removed, say, minus probability A and B, I removed it once. When I removed it twice, and I removed it 3 times. So I removed all 3 times which I counted them. The probability of the outcomes in the intersection of all 3. But it means that I didn't count them at all. So, and I need to count them. So I put them back. So kind of I put them back and write that this is equal to probability of A and B and C. Right? And now that's okay, kind of. Now this is the formula which works. So, okay, so which is why it's called exclusion, inclusion kind of formula. So you count it once, then subtract it, then look at maybe I subtracted too much, here you subtracted too much, and add them back. Okay? So this is a formula for free events, and in principle you can do it the same thing for any number of events. It just kind of will be exactly the same formula, but with more terms. And this is nice formula. Sometimes it's useful, but kind of we don't use it. But useful thing to know. So for our purposes, the most important formula is this addition formula. So kind of this is used constantly. All right. Any questions about it? So we will not probably do the example here, but it will be useful later. All right. So now kind of. So now we are going to, we already covered the set theory very briefly. Right? So now we are going to cover combinatorics. And the reason for that, so we are going back to Laplace times. So when every outcome have the same probability, right? And in this case, something which is called sample method is very useful. So kind of, I think this is called sample point method. I think it's called in the textbook. Sample point method. Right? And it's basically kind of the idea is that so in general, kind of it means that it's just use this formula. So kind of determine. So first determine the probability of each outcome. Probability of each outcome in event A, and second is add them together. So these probabilities together. And so it's exactly like it's exactly our rule. So the probability of A is equal to the sum of the probabilities omega I, for omega in A. Right? In the simplest case, kind of then total number of outcomes n, and all outcomes have the same probability. same probability. Then we have this formula. Probability of A is equal to the number of outcomes in A divided by N, the total number of outcomes. So this Laplace law. So now so that means that, so the, so this is the simplest case. And so in many cases, a classical probability, you just do this counting. Right? So so here's an example. So example, toss a coin. Question. Toss a coin 3 times. And so what is the probability to get 3 heads? Sorry, 2 heads. 3 heads is too simple, maybe. Okay, maybe 3 heads or 2 heads. So 2 heads. Okay, so now this is just example for this one. So first of all, we need to count how many of the outcomes in this experiment. So what the outcomes of the experiment? So, okay, so it's it's head, one possibility, head, tail, another possibility, so on, and tail. So these are all the possibilities. Okay, so it's easy to count how many of them, right? So the first time when we toss a coin, it could be head or tail, and so 2 possibilities. Second time, it's also head and tail, 2 possibilities. Third time, again 2 possibilities. So 2 times 2 times 2, so 8 outcomes. So right. So now all right. So now how many outcomes which have exactly 2 heads? So, and we will look at it in general, but in principle it's easy just to list them in this case. So it's head, tail, head, tail, head, and tail, head. So these are this is our event essentially, A. And so now the probability of A is equal to the number of outcomes in A divided by the number of outcomes, total number of outcomes. So so here's number of events here is equal to 3, so it's equal to 3 divided by 8. And so this is okay. So totally simple thing. Now so to do this thing, so the only thing that we need to do is to be able to count things, right? So count things in the event. And in general, it's a difficult problem. So we need to count things. And so the science, the mathematics of counting things is called combinatorics, right? So combinatorics. And in general, it's a difficult thing. So so I gave an example in the lecture notes. Not sure that I will repeat the formula right now, but say if you look at the problem of say tilings. So this is one of the fun problems, was to count how many ways to tile a chessboard by dominoes. Right? So now chessboard is 8 by 8, but here, so for simplicity, I draw kind of a board of 4 by 4. Right? And you can tile them by the dominoes. Right? So the domino have just 2 squares. The board have much more squares. So much more squares. So 8 by 8 board would have 64. And here's, and you can kind of look at the number of ways to tile the board with dominoes. And so now kind of it's doable kind of if its board is small. So probably, maybe, I'm not sure, but probably for 4 by 4 you can count it by hand, right, or using a computer. But if you go to the higher sizes of the board, then in this case with just enumeration, even if you have a computer, it will be difficult, right? So you'll need to figure out how to do the enumeration, but in general it will be difficult. So how many tilings by dominoes? Right, and in this case it's kind of difficult. So kind of it's probably one of the most amazing thing. One of the most amazing thing which was discovered, that there is a formula for the number of the dominoes. So you can easily see that if you kind of have a dominoes with an odd number of if you have a board with odd number of squares, you cannot tile it, right? But say, what about if you want to tile a board with 2n by 2n chessboard, right? And kind of, so the formula in this case kind of would be something like that. So it would be 4n squared, then a product here, j is equal to 1 to n, j is equal to 1 to n. So this is more general formula. I write just a variant of m when this is n and n. So this is a square when the board is square. And here will be something like cosine square j pi divided by 2n plus 1. And here's again, so cosine squared, so but here, sorry, should be k pi divided 2n plus 1. And so it's absolutely not clear why kind of this product of consent should have anything with a simple combinatorial problem like that. And so I think that this is kind of amazing formula in the sense that you cannot kind of find out how anyone could come up with this formula. Right? And kind of, so for so you can kind of calculate, so how many kind of using this formula it's possible to calculate, but it would be something like a product of a strange cosine, which when you kind of calculate it, strangely enough will be equal to the integer number. Right, so now another example maybe kind of how difficult things could be is that if you look at the number of the meander curves. So with the tilings, another example is meander curves. And so meander curves, it's just kind of, you have a something like a river, right? Let me see, something like that. Should be like that. And so which is so this is something like a path, and so this is a straight line, and when you go along this straight line, you cross a river, right, over the bridges. Right, and so now if you fixed this number of the bridges, so here's 1, 2, 3, 4, 5, 6, 7, 8. And so this is a 8 bridges here. And so you can ask the question of how many shapes of a river you can draw. Right? So how many many different curves, right? Passing say n bridges. Here's n is equal, so 2n bridges. So here's n equal to 4. And so now the answer to this question is not known, in the sense that no one knows the formula for this number. And so people know how kind of what's the asymptotic, so how it grows, not exactly, but knows. And we're able to enumerate it by computer for some kind of number of bridges. So it becomes very difficult when the n grows. And, but the formula, exact formula is not known. And all right, so kind of, so counting is difficult, but in our kind of, for our purposes, we'll just need kind of just the basics of the combinatorics. Right, so so we will not go in this difficult and very interesting question. We will just look at the basic tools. And again, so I think that many of you already have maybe seen these tools. So I just cover them fast, and you can go to for details to the book or something like that. Right? So, right? But we'll need to kind of to make sure that everyone knows how to do things. So what are these basic things? So kind of so basic combinatorics. Basic combinatorics. Okay, so first thing is the permutations. So and more precisely number of permutations. Right. I wanted to write number of permutations. Okay, so and so what is the permutation? So it's kind of a arrangements of objects where order matters. For example, you can have something like an object like, so let us kind of always old example, but maybe here in a different. So 1, 2, 3, 4, 5, 6. So 6 objects, 6 distinct objects. So here we look at the case when the objects are distinct. Right, so now, and so we're looking at the permutation of 4 of them. So that means so for 3, 1, and 6, 5 is not equal to 1, 3, 6, 5. And so this is a permutation of permutations of 4 objects out of 6 of. And so here's kind of 1, 2, 3, 4, 5, 6 kind of distinct numbers, distinct objects, and I can look at their permutation, but maybe not all of them, maybe just 4 of them. And so how many, what's the number of these permutations? So number of permutations. So in this example, how we can find it. So the first element could be chosen in 6 ways, right? So the second object, so 1 is already used, we cannot use it. It should be chosen in 5 ways, and so on, right? So kind of we end with the 3. Kind of the last one can be chosen in 3 ways. And then implicit here, we are using this rule, which is multiplication rule. So if you have some number of choices at the first step of the procedure, some number of choices in the second step of the procedure, and so on, we just need to multiply them and get the total number. Okay, so now here we'll get this one. In general, if n objects, then permutation number of permutations of R of them is, so the bucket code is P and R, and it's equal to n multiplied by n minus 1 multiplied by so on multiplied by, okay, so how many here should be n minus R plus 1. Okay, so in this example would be 6 minus 4 plus 1. Right, so right, so okay, so now again, so just a reminder, this would could be written with n factorial divided by n minus r factorial, where factorial is just a product of all the numbers. So n factorial is equal to n n minus 1, so on, times 2 times 1, right? So product of all of them. So here we'll have a n factorial, and we divided by n minus r factorial. So we remove every kind of term in this product before n minus r, right? So and we'll get this. All right. So this is the number of a permutation. Okay, so now in this example, we looked at the case when all the objects were distinct. Okay, so suppose that they are not distinct. I suppose that some of them could be the same. Okay, so now this example kind of from the textbook or something like that. So permutations when some objects can be the same. And in this case, okay, so the example in the textbook is this word Bobby. Right? So, so how many distinct words can be formed by permuting the letters. And so now kind of if you look at the previous example, so there are 5 letters here, right? There are 5 letters here, so, and we're allowed to permute all of them, so it should be 5 factorial, right? So there are 5 factorial permutations of the letters, right? But this is only if the words, all the letters would be distinct. Right? So we have something like a B1 here, B2 here, B3 here. Then the total number of permutations, if all the letters are distinct, would be equal to 5 factorial. Right? But since B are not actually distinct, when the words say B1, B2, B3, Y is the same as B3, O, B1, B2, Y. Right? So kind of a permutation among inside the set of the B's, and it actually doesn't change the word. And so, and we see that how many ways to permute these 3 letters, with 3B. It's 3 factorial, right? So every word, every distinct word corresponds to 3 factorial permutations of the letters B. And so if we list all possible permutations, then 3 factorials of them, kind of every 3 factorial 6. So every 6 permutation corresponds to exactly 1 distinct word. Okay, so we have 6 permutations permutations, which corresponds to the permutations of B corresponds to one word, one distinct word. Yes. Okay, so now when we list all permutation of the letters, it means that we overcount and kind of overcount by exactly the multiple of 6. Right? So we'll need to divide by this 6, and this 6 is 3 factorial. Right? So we'll get the total number of the distinct words is 5 factorial divided by 3 factorial. Right? So, okay, so, and this is kind of a general theorem. So kind of the theorem says that if the number of permutations of n objects, right? So in here will be 5 objects in which so there are k groups, right? And elements of each group are identical equal to okay, so here we'll write it n factorial, so it would be kind of a number of permutation without kind of, if all objects were distinct, divided by n1 factorial, n2 factorial, and k factorial, where what is this n1 into a k? So where n1 is the number, so maybe ni number is the number of objects in group I. Okay, so in our example, so what would be in our example? So in our example, we will letters B, kind of, this is the first group, then there was a O and Y. Okay, so this is another group, this is another group. So we will have here n1 is equal to 3, so n1 is equal to 3, n2 is equal to 1, and n3 is equal also to 1. Right? So the answer in our case would be 5 factorial, so sum of all these n's divided by 3 factorial and divided by 1 factorial, which we ignored because we kind of it's not essential, right? So the O and Y are the single elements in their groups. Right? So now in general, kind of the general answer is given by this thing. Right? Right? And this is called the multinomial coefficient. Right? So maybe kind of at this moment, let us stop. So, and we will continue just kind of a time for the break, and we will continue after the break. Right? So continue to talk about this stuff. It's a little bit kind of probably familiar to many of you, but it's we'll need to establish it. Right? So, and any questions kind of that you have, can ask now. Okay, so let me kind of maybe stop it for a second. Maybe we'll start in 5 minutes. So around 8:58. All right. Let's start. Okay. So, all right. So let us, okay, kind of. So multinomial coefficient. Okay, so definition. So multinomial coefficient. So it's just kind of the notation is that it's n, n1, n2, nk, right? And it's equal to n factorial divided by n1 factorial, n2 factorial, nk factorial. And just kind of again, so reminder that n factorial means that product of all the numbers n and smaller. So n times n minus 1 times n minus 2 until 1. Right? So here's kind of division. And here it assumed that n is equal to n1 plus so on plus nk. Okay? So in our example, it was just the number of the permutation of the objects, and some, not all of them are distinct. Right? So kind of if all of them will be distinct, it will be n factorial. Since not all of them are distinct, you'll need to divide by this, divide by this overcounting factors. Now, the most, well, one of the kind of, so this is a standard notation. Right? So one of the kind of important cases, so that it's binomial coefficient, right? So binomial coefficient, and it has a slightly different notation because it's very kind of popular. It came from the kind of, it has a slightly different notation, so it's denoted nk, right? And it's exactly the same, so it's by definition it's the same as n, k, n minus k. Right? So it's a multinomial coefficient that there are only two groups. Right? So one group has a k elements, another group have a n minus k elements. And so if you write the definition, it will be n factorial divided by k factorial divided by n minus k factorial. Right now, in principle, kind of, since here is n factorial, it's a product of large number of integers, and you divide it by n minus, say, by n minus k factorial, also a product of large number of integers. So, well, kind of, if you calculate it by hand and if you calculate on the computer, you will write it something like n minus 1, go and stop at n minus k plus 1, right? Because after that it will be divided by n minus k factorial. You don't need to divide it by n minus k factorial, just don't need to do a product. Right after that, and divided by, here's a k factorial, which is basically k times k minus 1 times so on times 2 times 1. Right? So just with n minus k factorial, I cancel it out on the in the numerator and the denominator. So now, so kind of an example of this would be something like a 5, 2 out of a 5. Right? So now what it this definition it says, kind of take the product on the top, and it's kind of, it means just take the 5 times 4. So it's just two terms, right? Exactly like the 2 here, and divided by 2 times 1. Right? So 2 factorial. Right? So in this particular case, it will be equal to 10. So you don't need to calculate, say, 5 factorial. Right? You just need to take 5 times 4, it will be 20 divided by 2. So it's very fast. Right? Another thing is, suppose I tell you something like a 100 100, and here is 98. Right? So calculate with binomial coefficient. Well, again, so you don't need really calculate 98 factorial, right? Just because if you look at this formula, right? So at this formula, and you see that in principle, kind of it's symmetric. So it's k divided by k factorial n minus k factorial. So in principle, it's kind of, you can, instead of 98, you can use 2. So it's equal to 102. Okay, so just in general, because in general you will have a nk is equal to n minus k. Okay, so it's because here is, the thing here is symmetric in k and n minus k. Right? So if you, so kind of it's by definition this equality holds. So 98 out of 100. So this is usually how it names. 98 out of 100 is equal to 2 out of 100. So it's equal to 100 multiplied by 99 divided by 2 times 1. So it's equal to something which is easy to calculate, at least easier than just calculating 98 factorial, right? So this is a useful thing to remember if you need to calculate it by hand, and also kind of even if you kind of have a calculator, right? So then in this case, well, you don't want to calculate 98 factorial, it will overflow your calculator, right? So in most advanced calculator, you have a binomial coefficient, and in most statistical packages, you also have a binomial coefficients and multinomial coefficients. And so it's, some of it is covered in the lecture notes, but it's kind of, well, so if you do the calculation, usually somewhere you can find a binomial coefficient. They are very important, kind of every software uses it. And another kind of thing is just kind of for fun, kind of, so these coefficients were discovered by Pascal, essentially, maybe kind of by other people before them. So kind of Chinese people, I think, discovered it much earlier, kind of, than Pascal, and Indian people is even earlier than kind of Chinese people. So kind of it's very, and so the kind of, here's the thing which is called Pascal triangle, because it was well discovered by Pascal, but maybe kind of by other people as well before him. So it's kind of, it's like that. So again, so many of you probably seen it. So it's 1 1, right? And after that, okay, so 1, here's the sum of these ones, 2 1. So here's 1. So 3 3. So the sum of the terms from above. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and 1. And it turns out that these are binomial coefficients. So here's 5, here's 10, here's 10, here's 5, here's 1. So you see that this is 0, kind of, this is n. This is n. So it's so kind of, if you count me, so this is 0, this is 1, n is equal to 1, this is n is equal to 2, this is n is equal to 3, n is equal to 4, n is equal to 5, right? And inside here is a k. So here's a k is equal to 0, here's a k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5. And this term here is binomial coefficient, k out of n. Right? So now, so the property says that nk is equal to n minus 1 k plus n minus 1 k minus 1. And it's also easy to prove from the definition. Can we just plug in the definition and check that this is true? Okay, it's just kind of, again, so mostly for fun. It's usually not used to calculate things, but it's interesting property. It was discovered by Pascal. Interesting that it was discovered by Pascal when he studied the problem from the probability theory. Okay. All right, so now Okay, so this is a binomial definition of a binomial coefficient, so maybe a little bit more about why they are useful. So one more thing, when they're useful in calculating the various counting problems. So suppose that you have a so this is a kind of problem of a partitioning. So let's look at something which is called problem. So maybe not problem. So it's counting how many ways to partition in groups. Right? Now, and here's an example. So suppose that we have some objects, distinct objects, and we want just to partition them in groups, right? So, and we know exactly kind of how many elements must be in every group. So here's an example. So we have, say, 10 kids, and we want to assign them to 3 classes. So class A has say 4 vacancies. This is class B 3 and class C also 3. And so altogether some kind of 10. Right? So now, so how many? So the question is how many assignments are possible. Right, and now here's a kind of a procedure how to kind of to do this assignment. So right, so now we can line up the kids. Right, so right, so we can say kind of the kids. So we can number the kids. Say, for example, 1, we have some number of kids, and after that we just line up them and say, so okay, so this is line consists of this thing. So it's 5, kid number 5, kid number 3, 1, 2, 4. Sorry, 4 already. 6, 7, 2, 1. Sorry, 2, 1 is already was. What we don't have 3. 8, 9, 2, 3, 4, 5, 6, 7, 8, 9, and there should be 1 10. So let me have a 10 here. Right? So here's a line of kids, and we'll just kind of look. Okay, class A have 4 vacancies. Let's take these 4 kids there. So class B have so this will be our class A, this will be our class B, and this will be our class C. Right, so now kind of number of all possible lines was 10 factorial. So, but after that we are saying, all right, it actually doesn't matter that there was a arrangement here was 4, 5, 4, 1, 2. It could be something like 1, 4, 5, 2, and it will be result in exactly the same assignment to the classes. We kind of this permutation in the beginning of the line, it doesn't matter, right? So, all right. So now turns out we'll need to divide by the number of permutation in the original portion of the line. So there are 4 factorial permutation of these kids, right? So now the permutation of these kids 6, 7, 3 also doesn't matter. So we'll need to divide it by 3 factorial. Permutation of these kids, well, we can kind of go around kind of in any order here, kind of, right? So we only think that we shouldn't go to the other portion into A and B. And it's also divided by 3 factorial. And we kind of see that we got again our multinomial coefficient, right? So it's equal to 4, 3, and 3. Right? And this is a general result. So kind of the theorem in general says that the number of ways to partition n objects in groups in, again, so k groups in k groups is this multinomial coefficient n and 1 and k, where ni is the number of kids in group I. So kind of, so well, this is a slightly different problem that we had before. And if you compare this problem, the first problem was that we looked at the permutation of objects, and these objects were not all distinct, right? And we will go to a multinomial. Here's a different problem where all objects are distinct, but the kind of the arrangement of the objects inside the group doesn't matter, right? So it's slightly different problem, but results in the same answer. Right? Now, one of the kind of important cases in this case is the case is in how many ways we can select k objects. So in our example, okay, so say 40 students in a class. In how many ways we can select a committee of 3 of them. Okay, and we assume that the kind of committees, the people in the committee absolutely kind of have the same role. So there is no kind of one special man, this is like a chairman of this committee. No, all the people kind of just should be kind of 3 people in this committee, and doesn't matter who is who, right, in this committee. There are no kind of chairman, the treasury kind of men, and so on. Right, and so they're kind of it's just a partitioning. It's a classic partitioning problem. We are selecting the people, 40 people, and we divide it in 2 groups. One group is a committee, and another group is not a committee. Right? So now you can easily write that this is a kind of this is a multinomial coefficient 3 and 37. Right? So this is the answer to this question. And now you look at this and saying that this is actually binomial coefficient 3 out of 40. Okay? So now kind of this is a problem of selecting of a subset. So selecting of a subset from the group. Right? And kind of so it's another result which is kind of corollary kind of. So number of ways, so it's again theorem, number of ways to select k objects out of n equals k out of n. right? And this is a this is a kind of the order inside this subgroup of object doesn't matter, and so this is different from our previous problem about permutation. This is kind of the selection. So in old kind of combinatorics, the selection is called a combination. This it was called before, and so this thing is called number. It's not only called binomial coefficient; it's also called a number of combinations, and denoted C and R. And so this is C and K. Sorry. And so this is old kind of name for the number of a combination, old name for the binomial coefficient. But this is exactly the same as a binomial coefficient K out of N. Okay, so now, so this is a kind of almost covered the combinatorics. So now one important thing we will use it not so frequently. Right? It was solving some problems which came from the times of the Laplace, but also kind of one example when it's useful is, let's look at our previous example. Remember when we throw a coin, right, and counted what was the probability that we got 2 heads. Okay, so now let us look at this example again more generally. Right? So toss a coin and let us say toss a coin 7 times. So it would be not so easy. Right? So toss a coin 7 times. So what is the probability? What is the probability to obtain exactly say 3 times? So for example, tail, head, tail, head, tail. It belongs to this our event, right? Because there are 3 heads. To obtain exactly 3 to obtain head exactly 3 times. Right? So we have exactly 3 times. Right? So this is kind of a good case. If we would have something like a tail, head, this doesn't belong to it because it's 2. And so now, so again, our recipe says it should be number of events. So probability of A is equal to number of events in A divided by the total number of events. Total number of outcomes, sorry. Number of outcomes in A divided by total number of outcomes. Now, total number of outcomes is easy. Okay, so it's so we can choose the first, the result of the first times in 2 ways, the result of the second toss in the 2 ways, the result of the third one in 2 ways. So it will be 2 times 2 times 2 times 2 and 7 times, right? This is possibility for the first toss, this is possibility for the second toss, this and so on. So right, so 2 to 7. So this thing is 2 to the power of 7. And now what the interesting thing is how to calculate the number of the outcomes in the event. And it's also easy. So it means that we have this is the result of the first toss. This is the result of a second toss. This is the result of a third toss, and so on. Right? So 7 of them, and we'll need to decide when. We need to decide in which of these tosses we've got a head. Right? So there are three kind of there should be 3 tosses in which we obtain a head. Right? And if I decide that it was here head, and say head, right? Then you know that in all other cases it should be tail. Right? Because if these outcomes belong to A, then kind of in 3 of the tosses should be head and all others should be tail. Right? So if I decide in which of the tosses was head, then kind of in all others was tail. Right? So the thing is that I'll need to divide these tosses in the portions. In the first group heads, there should be 3. This should contain 3 tosses. Right? So right, the other group should contain 4 tosses. Right? So now if I decide that heads are here, then all others should be tails. Right? So I should put here tail, 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 tail. And this is our partitioning problem, right? So I have a kind of, 7 objects, and I need to decide which of them will be in the group which contains heads. Okay, so now kind of I decided it should be this should go to this group, this should go to this group, and this toss should go to this group. Here, this is the group of heads. All others is a group of so it's a problem of selecting of a committee of a kind of tosses, selecting kind of which tosses will be heads. Right? So now kind of I easy kind of conclude that it should be okay. 7 tosses. I selecting 3 of them, so it's 3 out of 7. Right? So this is a kind of this is our this is the number of outcomes. This is the number of possible selections of these things. So it's number of outcomes in the event A. All right. So now kind of so the probability will be equal to A divided by omega. So it's equal to 3 out of the 7 divided 2 to the power of 7. Right. And in general, if we toss a coin n times, the probability to get k heads is okay, so k out of n. Okay, so number of ways to decide which of these tosses were heads divided by 2 to the power of n. Okay, so, but this is only under the Laplace definition that all outcomes are equally probable, and so on. All right, so this is one of the first application of all this stuff to the probability theory, probably the most important application, but because we will use it after that. Okay, so we probably should stop here. Next time what we will do, we'll look at a couple of problems in probability theory, which uses this methods, combinatorics method, just kind of calculate several probabilities using these combination coefficients. And we should go, hopefully we will go beyond that. So that means, well, kind of what to do if, so what is the other method? So suppose that you kind of either cannot count these events or kind of in the situation when the outcomes are not equally probable. So is there any other approach to the probability theory? And we will talk about the fundamental things such as a conditional probability and independence, hopefully. So we should do it. So next time is a couple of the problems from this combinatorial probability, and after that the conditional probability. All right. Okay, so any questions? Hope it's okay. So if I'll close this thing. If no questions, so we will see you guys on the Friday.
Thank you, Professor.
Thank you, Professor.
Nice
Thank you.
nice.
Thank you.
Thank you. Have a good day.
Thank you.
Thank you.